I welcome everyone here. I know it's very late in the conference, and resiliency and reliability always has to take like a last session because it comes at day two. But over the next course of 20 minutes, I'm going to convince you that this is a day zero problem for many of the GPU infrastructure builders. And I'm Prashant, AI engineer working for Clockwork Systems. Who are we? So we are a small startup based out of Palo Alto, California, originally spun out of a Stanford lab project. And we have industry luminaries as our VC partners. And also we have co-founders that comes from all the areas of boring computer science problems such as distributed systems and storage and networking and virtualization. So we have a strong background in virtualization. We are here to democratize the journey of high performance networking and how to bring in more visibility, resiliency, and sort of performance optimization on working on any NIC, any switch, and any sort of hardware without any hardware dependencies. We want to be vendor agnostic. So that's our mission. So AI training, as we know, it goes through a series of both training and communication, right? So the training splits down into compute phase and communication phase, and communication is becoming even more bigger bottleneck than compute as GPUs get faster and faster. The overload is on the network to be high performance. So that's the predominant problem that the infrastructure operators and also model builders are dealing with today. And today we can see more than 30 to 60% of the time to train models is spent on networking. So, and this networking is sort of a little bit different, right? So they have a dedicated backend network that that talks over a series of NICs as a backend fabric so that other traffic doesn't interfere with this sort of GPU to GPU networking. And second, the protocols need to be highly lossless and high bandwidth and low latency. Typically, people use Rocky V2, right? RDMA or converged Ethernet or InfiniBand if you're going with the proprietary solutions like NVIDIA. And training code, typically like when you're using PyTorch, they use like Nickel, or if you're on the AMD's infrastructure, you have to use RICL. So you'd be hearing these terms more often in my talk. So Nickel, if folks don't know, is NVIDIA's collective communication library that establishes this communication pattern on a highly distributed infrastructure training. And this is what coordinates all sorts of communication that's going on the network. And any sort of jitter in this network is going to disrupt your entire training job. Imagine, you have a cluster of 10,000 GPUs, highly synchronous training that's going on, one optic flap. That's all it takes. One optic flap, the entire job's crashing. Sometimes not all flaps, is going to cause problem, but 10 to 15% of the flaps can lead to fatal job crashes, right? Okay, so I was talking about the network failures, right? So it's very disruptive for your synchronous AI communication. And typically when the infrastructure guys, when they're operating this GPU cluster, there are plenty of gaps in debugging these problems, right? One is visibility gap. What's going on in the network? What's causing this slowdown, right? There are tools, right? But they are very disaggregated. For example, GPU guys, they operate in like GPU world. And networking guys, they come from the switch's point of view and they sort of understand the traffic from that point of view. There's no way that there's a cross-stack visibility from your host compute to the networking layer. So that's one problem. The second thing is resiliency gap. So if something goes bad, how am I able to come back from that failure? How am I able to save all the valuable GPU compute time that I've been through so far? Right. The third one is performance gap. This is a shared networking infrastructure. So there's multiple guys who's training on the same network. If you're going on a cloud, say Neo Cloud, right? GPU cloud, they're going to share the same leaf spine networking layer, and they're going to cause interference, and this eventually going to cause congestion, and you're going to see, variable training times and also job completion times. Overall, you end up getting lower GPU utilization because you're spending more time on the network and longer job completion times and lower return on your investment. This is a popular study widely published by Meta guys. Right? This is during Llama 3 training. How many times their jobs got interrupted? It's almost like 10 times every day. So this is 16,000 GPUs, H100s, right? 466 job interruptions. out of which predominant bucket is GPU failures and memory failures. But the next one close to the GPU failures is network failures. Network failures fall into this bucket of like, optics, which is pluggable optics, flapping or failing, or NIC card failures, and also nickel timeouts. This is high-level software libraries timing out because it's not able to rendezvous the other process. So overall leading to quicker time, longer time to recover, first of all. Second, inconsistent iteration times. Third, increased GPU costs because, the time you're not using GPUs, you're getting still billed, and overblown compute budgets for bigger labs. So this is an industry-wide problem. And there was a talk from OpenAI 2 days ago from their hardware team that talks about why networking is an important problem, especially, optics failure and flapping. Not just me, several analysts in the area, like semi-analysis, also talks about this problem, right? So bigger your GPU compute is, quicker you fail. Because, on a cluster of 50,000 GPUs, the first failure can happen even in the first half an hour of starting a job. That means you're increasing the frequency at which you're checkpointing. The bigger the model, bigger the risks are. So you have to checkpoint often. And every time you have to restart from a checkpoint, right? Say if you're checkpointing every 2 hours, you're almost have to restart. And there is a cold start for all your traffic, like CUDA to warm up. And also it's going to cost like, a lot of engineering hours to debug what the problem was, to bring back the cluster state, or to get a brain node available, first of all. And to root cause it is also a bigger problem. So networking is becoming an important problem in the area of training. Further, AI jobs can also fail silently, right? The failures might not be obvious. The jobs can keep on going, but you like if you have trained the AI model, right? There are sometimes some iterations takes, say 5 seconds, and sometimes it takes 8 seconds. What explains that, plus 3 seconds, right? It means there is some guy in your distributed training that's limping along, maybe because of slow storage, slow network. So are there any tools to attribute why that happens, right? So these failures are invisible to the end users because, this happens in the back end of the GPU to GPU communication layer. And failures also repeat if it's not fixed properly. I was just talking about the back-end fabrics, right? The networking is all over the place. There is also front end, right? People build front end dedicated for storage to GPU traffic. So this is the network that, the training guys use to sort of like recover and load checkpoints and also load data before the start of the training. So that needs to be dedicated as well. So the performance of that needs to be protected, and the QoS of that also becomes important. So there are several middle level communication libraries. For example, Nickel, as I was talking about, it's for GPU to GPU communication. And for example, for storage, there is GDS, the NVIDIA's library, right? GPU direct storage. So there is a lot of abstraction layers that's introducing even more complexity that these tools are not able to pick up what's going on, right? What's going on in your backend network. So the communication is kind of slowing down the entire training problem. And that's because there's stringent IO demand. There's the whole nature of the problem is stateful and synchronized. And there's multiple transport layers involved depending on which switching vendor you're using. And there's frequent hardware failures. So overall, it's leading to slower job completion times, lower return on investment, and lower model flops. So we at Clockwork want to redefine this problem. Right? How are we going to do that? Right? We want an always-on resiliency layer that looks at what's going on in the backend GPU of how each GPU is talking to each other over the NIC. So we are deploying always-on probing to understand what's going on in the network real time. Right? This is bringing in an insane level of visibility of your backend network traffic. The second thing is we are able to deeply embed ourselves in RDMA protocol, which is remote direct memory access protocol, to understand where the load is going, how it's congested, and can we do something about it. It's all in real time. And we're also able to exert control on these RDMA to sort of like monitor performance, and also maybe if there is a chance to accelerate performance if we detect congestion or contention. So And on top, we want to be purely software, and we want to be vendor neutral. We want to work with all AMD, NVIDIA, and all sort of switching and NIC providers. So we are very excited to share about our product, which is Fleet IQ. What it does is threefold. One, it's bringing cross-stack visibility. What's happening at the GPU level and what's happening at the network level, we're able to make sense of both of the things and sort of like accurately say, hey, this is where the issue is coming from. Like it gets to the root cause of the problem much more quickly. And second is stateful fault tolerance. Failures are common, right? So when these failures happen, how is your AI workloads protected from these failures? How is it statefully managing these failure states and sort of like reroute or redirect with relevant resources on the same node? So that is one more feature that we're bringing in. The third one is efficient performance. How are we able to detect and mitigate congestion and contention in your RDMA networks? So those are the three things put together. It's getting us faster job completion times, always on resiliency, and higher output per dollar. So anyone who's operating like a large scale GPU infrastructure would get benefited, be it enterprise or be it neo clouds. Fleet IQ brings in insane visibility to your backend networks. How are we doing this, right? So there's GPUs. It's a distributed cluster. And there's front-end NICs that I was talking about, where storage to GPU communication is happening. And there's back-end NICs, where GPU to GPU communication is happening. We're able to synchronize the clocks on all these elements across the cluster to a global reference. So only with which we are unlocking this observability piece, where now you can calculate one-way delays from one NIC to another at any given network, right? Be it front end or back end, we are able to figure out through our probes, continuously monitor which is more congested path. Is there any potential path that we could use to route the traffic? So second thing is we are also able to do the same thing for the backend network. It's all possible because our clock sync insanely synchronizes the whole clocks to a close to like hundreds of nanoseconds. So that's why this level of observability is possible. Further, the backend RDMA networks that this backend network is using, we're able to go up to all the way up to the message and chunks and queue pair level latency, where we are able to figure out from the send receive queue pairs of the RDMA, which queue pair should I use, right? So to sort of like accelerate my performance. So this is all happening at the real time. So enough of theory, right? Let's go into the demo. This is our UI. Before I play this UI, this was a live demo recorded on Oracle Cloud, right? What we are seeing is 4 GPU nodes, and each GPU node has 8 A100 GPUs, because of the cost. And each GPU is associated to 2 logical NICs. So that's why you're seeing 16 NICs here, and there are 8 GPUs that's sitting on these nodes. You see 16, 16, 16, right? There are 4 nodes. So why these are on green? Because right now our probes are saying that the one-way delays from each NIC in this rail optimized communication is less than 25 nanoseconds. Again, that is user defined. So depending on how close or how fine granular your adjustment needs to be, you could customize that too. So we're calculating edge to edge delays here. So we're able to plot all the way up to the queue pairs of RDMA, where we are creating 4 queue pairs out of band, and we are showing the one-way latency close to few hundreds of nanoseconds. So one more information that I need to add here is the first 2 are in the same rack. The second 2 nodes are on a totally different rack. So it has to go through a shared leaf spine. Okay, let's launch a job now. All reduced, right? This is a popular nickel collective where GPUs are exchanging weights. That means each NIC, which is capable of doing 100 gig speed, is going to send data. This is a collective that goes on the distributed training. Now we are waiting for the traffic to pick back up. So each NIC can do 100 gigs. So totally 1.6 terabits per second is possible. So we are doing all the way up to 1.4. This is happening on the network, and each NIC across its queue pairs, it's able to do close to 100, right? It's 92 gigabits per second. And we are monitoring edge-to-edge latency here. So you see the Q pair one-way delays have gotten a little bit up because there's load now, and we are measuring it close to 3 microseconds. So what I'm trying to do here is trying to simulate a NIC flap. This in a real world environment could be like an optics failing because of heat, thermals, badly seated optics fail all the time, right? So when I do that, what happens, right? Our probes are able to not talk via the NIC, so the entire job kind of like, it's not able to send its data out, so the entire job crashed. So this is what happens in today's synchronous training. Right? So one NIC failing or one NIC port failing out of this 64, NIC setup, it's going to bring the entire training to an halt. This is the problem. Then the NIC comes back up. Say it's a temporary failure. Nothing is going to happen unless there is some coordination from your, low level to your nickel, to your PyTorch, to your all the way up to Slurm to restart all the jobs, to redo all the work, to start from a checkpoint, and there is a warm-up time and warm-up cost to it. So this is the state of the art problem today, which large training labs are going through. We're going to do the same experiment with our plugin, right? We came up with a plugin that works on top of both nickel or RICL, just a shared object library that you have to use as an environmental variable before you start training, purely software, right? So that's going to go now. So the traffic now, we are going to rerun with the plugin, and it's going to pick back up. We'll see the traffic back up again to 1.5 terabits per second. And we are going to simulate the same NIC flap with our plugin. Right? The overall throughput is now 0. The job has launched. Let's wait for the traffic to pick back up. It's again started picking back up. So the NIC is again doing, all the NICs are doing close to 100 gigs speed. Now let's simulate the same NIC flap, which is like a port down that I'm doing. So our probes are able to detect the NIC is down. So in real time, it's able to reroute the traffic with other healthier NICs on the same PCI root complex to sort of like reroute the traffic. And that way the NICs on the same node is picking up the slack, that the failed NIC has left to sort of like gracefully move the traffic out of the job. So now at the job level, it's as if nothing happened. Right? The jobs are continuing to train. They have not failed. This is happening at the real time. Now say the NIC is back up, right? We are able to detect connectivity again, right, through the fabric that we are deploying. So it's back up to the green. Now the traffic should be able to pick back up to its near theoretical peak, right? So that's the level of fault tolerance that we are enabling through Fleet IQ. So now the NICs are back up again. So you see that NIC that went down, now it picked back up in the traffic, and all the NICs are able to do close to 100 gigs. So this is one part of the product that talks about fleet resiliency, right? I'm going to do the same demo for performance acceleration. What is performance acceleration, right? Say there is like a shared noisy neighbor on your cloud, right? This is a public cloud, Oracle cloud. Say you're sharing the same networking infrastructure, which is high performance, but still you're launching competing traffic on the same lossless link. Immediately you're going to see congestion. So what we are showing here is the NIC to NIC one-way delays are going up more than 25 microseconds. Now, both of these jobs that I'm launching across rack is competing for that bandwidth, and none of it is able to utilize the link bandwidth properly. It's almost close to half. Like it could do 1.6, it's only doing 600 to 700 gigs. So each NIC is capable of doing 100 gigs, but it's only doing 50. So this means your AI jobs are straggling, right? Your iteration times is going to take longer and longer to sort of like understand what's going on. That's again translating to elevated Q pair latencies in RDMA. So individual queue pairs that the workload is using is going up in terms of latency. So on one channel, there are 8 queue pairs, and every one is getting busy because there is traffic going across the shared spine. Right? So once we bring in our control, so we have an ability to exert control to understand this congestion and figure out what are the potential routes that we could take to sort of like mitigate this sort of issue, right? Interference. Once we have a once we have our control on, both the workloads are able to do better, right? It's going to go back to near theoretical peak. That's because they're able to find different routes on the same shared network, migrating their traffic to a better queue pair. We call this route scout, right? So it's able to find those routes and automagically, I would say, rerouting the traffic to a healthy and relevant, less congested queue pairs. So you see, it kind of goes, it's like a denoising state. It's like active noise cancellation on versus off, right? So we are able to greatly minimize the divergence in sort of like one-way delays in your entire network. So this is the level of visibility that our tools could bring in today's AI fabrics, and with which we can get in both stages of provisioning, which is day 0, and operations, which is day 2, right? What we are enabling is fleet audit. Once you bring up a cluster, you have to do all sorts of software checks, node checks, and posture checks, in general, validating whether all the networking infrastructure is alive and responding, both in terms of front end and back end. Second, it's continuous monitoring through our probes. So our probes are running, like we are sending thousands of UDP probes, which are very lightweight, right? It doesn't take up bandwidth of your RDMA network, and continuously sensing what's going on in the network, and is able to plot a real-time telemetry, hey, whether I'm able to reach all the NICs in the same rail. Right? So it can detect runtime NIC flaps, validate the fabric topology, and also monitor for contention and congestion. Third one is, that's out of band, right? We can also experience what workload is experiencing in band. Right? We're able to exert ourselves on top of Nickel, which is NVIDIA's collective communication library, and provide deep visibility of what's happening inside the workload, and should we actually steer these RDMA queue pairs and do this active noise cancellation, right? It's kind of like a digital twin of your backend network fabric in real time that you're observing what's going on. Gives a lot of sense to attribute for failures, get your models faster to sort of like production. So let's make AI resilient together and build with Clockwork. Today, we are talking to a lot of exciting enterprise customers such as Uber, Zoom, and LinkedIn. They're all using this software internally on their GPU fleet to sort of understand what's going on their backend fabric. And we're also partnering with several known neoclouds in this area to bring resiliency to become a day 0 operation. So if you're interested in talking to us, please reach out. Thank you.